So now for another slightly nice example. This is again a second order differential equation. And if we recall, we sort of started out with having z squared here for the Bessel equation. And for that to give us something with regular singular points, we have to have some multiple of that here, and then just anything here. Well, we're now going to do a slightly more permissive case. Namely, we say, okay, well, the thing in front here doesn't really need to have like second order zeros. We can just have it have first order zeros. So why not have the zeros be at 0 and at 1? And then here we have just some other first degree polynomial, because why have it be of a higher degree? So cz plus d, and then just a constant here. But we are already going to slightly rewrite things, because, well, firstly, d plus cz, and then why not write c as 1 plus a plus b and e as minus a times b. You can still sort of generally find a and b that always capture this special case, or this general case. And then why not call this variable c instead, and maybe a minus there. So what we are really doing is look at this equation, and the keen viewer might recognize this as the hypergeometric equation. And this is really the most general equation of the shape second degree polynomial, second derivative, first degree polynomial, first derivative, constant, just a function. Sort of just up to affine transformations of z itself. Well, unless you have a double zero, in which case you can't transform it into that shape. Never mind. So this function has, if we divide it through by z1 minus z, has regular singular points at 0 and at 1, and also at infinity. So, in theory, we could write it as a series around 0, around 1, and around infinity, and then it will turn out that a bunch of them will be the same. Never mind. So we again have our Frobenius ansatz, that g of z be some power series where the powers are slightly fudged. Again, the same derivatives. And if we plug this in, we get minus z squared second derivative. So in this case, the powers do add up to z to the n again. The same happens for z and the first derivative. So plus a plus b plus 1 and also for the constant term. And then we have plus n plus r n plus r minus 1 a n z to the n plus r minus 1, And here we have the same thing with the C in front. So we really only have to index shift these terms there. And we can also put the first ones already together. N plus r minus 1 minus n plus r a plus b plus 1 minus ab. And then we have r times r minus 1 a naught plus c times r a naught times z to the r minus 1 plus from 0 to infinity n plus r plus 1 n plus r a n plus 1 z to the n plus r, and yeah, then plus c n plus r plus 1 a n plus 1. So pulling all of this together, we get r times r minus 1 plus c a naught z to the r minus 1, and then a giant sum. We have n plus r minus 1 minus, okay, we can really put these together, plus a plus b plus 1 minus ab an plus, and then we have n plus r plus 1 times n plus r plus c an plus 1 z to the n plus r. And that this is 0 now means that r times r minus 1 plus c is 0, and that n plus r well, minus 1 plus r cancel out, plus a plus b minus ab an plus n plus r plus 1 n plus r plus c an plus 1, but this is 0. And we, well, this is n plus r squared plus a times n plus r plus b times n plus r plus a times b, which is n plus r plus a times n plus r plus b. In other words, we have an plus 1 is equal to n plus r plus a n plus r plus b divided by n plus r plus 1 n plus r plus c times an. And from our initial equation, we get that either r is 0 or r is 1 minus c. Yeah, if we now iterate this, we see that sort of for every step we go down, we acquire another 4 of these factors, but each time with a different n. And we can again write this in terms of rising factorials, and we will find that an is equal to a plus r n b plus r n c plus r n 1 plus r n times a naught. So then we get as our solution a plus r n b plus r n c plus r n 1 plus r n z to the r plus n for r is equal to 0 or 1 minus c. Now let's now look at the case of r equals to 0. So for r0 we have an, bn, cn, 1n, z to the n, and because this function actually comes up a lot, it has a special name, namely it has the name 2f1 of a, b, and c evaluated at z. The reason why, well, a and b are on top because they are on top in this fraction, c is on the bottom because c is on the bottom of this fraction, and then 2f1 because we have two functions on top and two factors on top and one factor at the bottom. So big surprise, the solution to the hypergeometric equation is the hypergeometric function. And now what happens if we pick 1 minus c for our r, then we get a plus 1 minus c and b plus 1 minus c and c plus 1 minus c and 1 plus 1 minus c, so 2 minus c n, and well, the c's cancel here, z to the 1 minus c plus n. So if we factor out a factor of z to the 1 minus c, we see that we still get a hypergeometric function. So this is z to the 1 minus c times the hypergeometric function, well, not of the parameters a, b, and c, but a plus 1 minus c, b plus 1 minus c, and 2 minus c. And those are our two solutions.